Hello everyone, and thank you for joining us for our final project presentation for AE 6362. Our team, Group 3, has conducted a comprehensive preliminary aircraft and system safety analysis of the KC-46 Pegasus tanker. This aircraft plays a critical role in the United States Air Force's aerial refueling capabilities and presents unique challenges and considerations in functional safety analysis. Over the course of this presentation, we'll walk through our approach using the ARP 4754 and 4761 methodologies, discuss our vehicle-level functional hazard assessment, system-level safety analysis, and conclude with fault tree and Petri-net models that reflect the operational safety profile of the KC-46. Our team members are Zachary Connor, Chad De Montfort, Reed Esper, Matthew Kraus, Sam Landers, and Justin Penev. Okay, so let's establish what aerial refueling is and why is it done. Aerial refueling is the process of transferring fuel from one aircraft, the tanker, to another aircraft, the receiver, in flight. The concept dates back over a century. In 1923, the United States Army Air Service performed the first successful fuel transfer between two DH-4B aircraft using a hose. This laid the groundwork for what would become a critical capability in modern air operations. During World War II, aerial refueling was used in a limited capacity with modified B-24s serving as tankers for B-17 bombers. However, it was really during the Cold War that aerial refueling became a cornerstone of nuclear deterrence, enabling strategic bombers to reach targets across the globe without relying on forward bases. Today, aerial refueling is a ubiquitous capability adopted by nearly all major air forces. It serves not only as a force multiplier, but also as a key enabler for global power projection. The primary purpose of aerial refueling is to extend the operational range and flexibility of aircraft, eliminating the dependence on intermediate basing.
In their search for a new air refueling asset, the Air Force awarded the contract to Boeing to modify their Boeing 767 into the KC-46 Pegasus. Here you can see a list of its features, capabilities. In addition to the features and capabilities laid out in the previous slide, the KC-46 has many aspects that make it advantageous. It has a larger refueling envelope, centerline drogue system, nuclear, chemical, and biological hardening, flight deck armor, and also has the capability for aeromedical evacuation, among other features. Like other tankers, the KC-46 has a mission profile and range that fit under normal standardized guidance under the FAA and even ICAO. Another important aspect of the mission profile is the aerial refueling itself. Not only does the KC-46 need to consider its own fuel to accomplish the mission, but also what fuel it would be able to loiter with while waiting for receivers to come receive the gas, and also how much gas it will give to other receivers. All of this makes the mission set of the KC-46 somewhat complicated. Now let's pivot to the preliminary aircraft safety analysis of the KC-46. First, the requirements were laid out succinctly by the DoD in their Selected Acquisition Report, or SAR. Here you can see several characteristics that were required of the contractor and the capabilities associated with these characteristics. With both the requirements from the previous slide as well as all of the features and capabilities from earlier, we can complete the aircraft functional decomposition of the KC-46. Please note the box that's highlighted for provide aerial refueling capability. This will be our subsystem of interest through the remainder of the presentation.
This diagram shows the top-level functional architecture of the KC-46 Pegasus. Among its key mission functions, we've selected Provide Airborne Fuel Transfer as the focus of our preliminary vehicle safety assessment. This function includes establishing stable geometry with the receiver aircraft, initiating and regulating fuel flow, and safely disconnecting. It directly ties into other core functions like flight control, propulsion, and communications, which we also considered when modeling failure modes. This continuation slide expands on supporting functions related to the target airborne refueling capability. The important one is provide fuel storage and management, which handles storing and routing fuel to the refueling system. Other functions like self-protection, ice mitigation, and payload stability also influence the reliability and safety of mid-air fuel transfer. These supporting functions were included in our hazard assessment to fully characterize systematic risk.
Now that we have identified the major systems of a vehicle, we are allocating these logical systems to the functions. Highlighted in yellow here is going to be the subject function of our PSSA later on.
This first view of the physical architecture zooms in on the hardware components tied to our selected function. The air refueling system shown in gold includes the boom, vision system, control sticks, hydraulic actuators, and fuel transfer valves, all of which must operate in harmony during mid-air refueling. We also highlight related elements from the electrical power system, such as the APU and TRUs, which power mission-critical avionics and fuel systems. Finally, components from the environmental control system, like temperature sensors and oxygen supply, ensure mission readiness and operator safety, particularly for the boom operator station. This continuation slide is an emphasis of the fuel storage and management system, which plays a critical role in supporting the aero refueling function. Highlighted in gold are systems like the wing tanks, fuel pumps, fuel management computer, and overpressure protection systems. These ensure that the fuel is safely stored, measured, and transferred under dynamic flight conditions. Other critical interfaces include fire detection and suppression systems, which help mitigate hazardous fuel leak scenarios, and ice protection systems, which are essential for maintaining safe operability during high-altitude refueling operations. This slide shows the vehicle-level functional hazard assessment for the KC-46. In addition to our target function, we included supporting functions like propulsion, flight control, guidance, and communications. For each function, we identify potential failure conditions, their aircraft level effects, and assign severity, development assurance level, and likelihood. For instance, failure to disconnect fuel transfer is classified as catastrophic, while uncommanded fuel offload is hazardous. This assessment establishes the vehicle-level safety targets used in our downstream system analysis. Here's a continuation of the FHA with supporting systems such as environmental control, fire safety, landing gear, and fuel management. Hazards like cabin depressurization or oxygen loss are classified as catastrophic due to the threat to crew survival. Other risks include fuel tank overpressure or ice protection failure, both of which can cascade into mission failure. These failure modes provide the foundation for our later system-level safety analysis, including fault trees and independence evaluations.
Moving on from the FHA, the risk assessment matrix presents the FHA analysis in a more visual format. As you can see from the template, as severity and likelihood of failure decrease, the impact of the risk to the aircraft decreases, as seen in the green lower corner. As the severity of the risk and the likelihood of the event happening increases, the impact to the aircraft does as well, culminating in a catastrophic impact shown in red in the upper right-hand corner. The risk assessment matrix for the KC-46 is shown here. The results from the FHA show mostly medium impacts in the yellow band that will need to be mitigated. Anything from catastrophic, but extremely improbable, to minor and reasonably probable are in this band. The impacts of tire burst and incorrect software load are the most major impacts that the team highlighted and are shown in the orange band. These are major and reasonably probable likelihood of happening.
The common cause analysis can be completed in two different ways. The first is the particular risk analysis. Here, in either a bottom-up or top-down approach, threats to the system are identified as either coming from the environment, operations, or even its design. They're explained in ARP 4761 Appendix L, but in the case of the KC-46, these hazards tend to be generic and affect all airplanes. Because we chose to focus on the aerial refueling system of the KC-46, a zonal safety analysis is more appropriate. Here we chose a particular system or function and drilled down into different safety hazards associated with the system. In a diagram straight from the ARP 4761 Alpha, we identify the air refueling components on the airplane. The subsystems include the air refueling operating system, air refueling boom, multi-point drogues, and the cross systems include the fuel, hydraulics, electrical, and flight controls. All of these cross systems affect the operation of the air refueling system.
Target levels of safety establish what the safety target is for the Air Force flight operations. Since this is a commercial derivative aircraft, it should meet or exceed the commercial aircraft operating in FAA airspace requirements. The TLS establishes a quantifiable acceptable risk level for the operation of the aircraft. Our TLS dictates that there shall be no single point of failure and that the probability of the second failure is 1.0 times 10 to the negative 9th. On the right, you'll see a safety assessment process with the TLS establishment circled.
This slide shows the fault tree analysis performed for FHA Hazard 1.2, partial loss of thrust. It includes safety metric values, which are very much estimates at this point in the design process. Values were input for the failure rates of each event, and the software calculates the risk at the top gate based on the tree's gate structure. The lower level reliability can be adjusted until the risk matches the FHA probability objective, as long as it doesn't exceed that value. And ultimately, this would be an iterative process throughout the design cycle as testing and validation are performed.
The fault tree analysis that we see here is for the air-to-air refueling capability. Within this capability, we have the possibility of a boom capability failure, a drogue capability failure, or a fuel transfer failure. Both the boom and drogue capabilities are OR gates with 2 OR gates below. The 2 OR gates below represent a mechanical failure or a control failure. At the bottom of the slide, we see a series of vents, and with the OR gates that make up the overall air-to-air refueling capability, we can find that if any event occurs, the entire capability will fail. This slide shows the reliability block diagram for the air-to-air refueling capability. Each of the blocks on this diagram represents one of the events described on the previous slide. And as stated previously, if any of the events occur, then the overall chain will be broken and the air-to-air refueling capability will no longer be available. Here is the fault tree for the complete air-to-air refueling capability. This is an expansion on the one previously shown, where we have added an AND gate between the air-to-air refueling capability and the boom and drogue capabilities. This implies that for the complete air-to-air refueling capability failure to occur, we would have to have both a boom and drogue capability failure or a fuel routing failure. In some mission scenarios, the KC-46 can be retasked to switch between utilizing its boom and its drogues to refuel aircraft. And this represents what happens when both of those capabilities are no longer available. Similar to the first air-to-air refueling capability, we have created a reliability block diagram for the complete air-to-air refueling capability. The difference here is that the failure events for the boom and drogue are placed in parallel with each other and followed in series by the events for a fuel transfer failure.
For our preliminary system safety analysis, we chose the aerial refueling capability as it is unique to this aircraft. This capability interfaces with many systems on the vehicle, such as the aerial refueling system and the fuel storage system. It also performs multiple functions, provide airborne fuel transfer and fuel management system. On this slide, we show the aircraft functional architecture for the KC-46, where we are targeting the function provide airborne fuel transfer for the PSSA. This slide also shows the functional architecture for the KC-46. This time, we are highlighting the provide fuel storage and management functions as well. Now looking into the allocations of those functions, we are specifically targeting the aerial refueling logical system here, and those directly associate with the functions that we identified on the last two slides. Continuing with the last physical architecture slide, we're now highlighting the fuel storage management system as well for the PSSA.
Similar to the vehicle safety analysis, the system safety analysis also includes an FHA. This begins on the left-hand side with the function names, followed by the failure conditions and their effects. The next two columns represent the severity to the KC-46 as well as the receiver aircraft. Then we see the allowed likelihood for each of these failures and the probability objective. The next step in the system safety analysis is to identify the item development assurance levels. We start with the physical architecture items and the item type, and then we bring in the worst severity from the functional hazard analysis before identifying the assurance level and defining the independence requirement. In the upper section, we see the items that are required to transfer fuel between the KC-46 and a receiver aircraft. In the lower section, we see the items for holding and moving fuel within the KC-46 itself.
Our PSSA focuses on the Provide Airborne Fuel Transfer function, which directly supports the KC-46's primary mission. This function is tightly coupled with Provide Fuel Storage and Management, so both were selected for our fault tree analysis. These functions were traced from the functional architecture into physical components, allowing us to model their failure paths systematically. The next slides show how we decompose these functions into Boolean logic branches in the FTA.
Our team's first FTA for the PSSA focuses on the overall fuel transfer capability. The overall complexity of Boolean logic will expand from here, as this page focuses on the highest level logic. From here, we can see how the base events for the FTA are broken out into groups for a reliability block diagram. It is realized that the AAR capability heavily relies on mechanical, software, and electrical components to be reliable, as there is a lack of independence between those subsystems.
Okay, so due to the limitations in the item toolkit software evaluation period, we split the full fault tree analysis into 3 branches. The diagram here shows our top level structure with 3 main contributors to total failure: electronic management system faults, loss of storage capability, and loss of transfer capability. These are each modeled as individual fault tree branches, and we'll walk through them one by one on the next slides. This is the electronics branch of the fuel system FTA. Here we see that failure of the fuel management computer or wiring causes system loss. We break this down into specific failure modes, such as logic errors, power supply failures, sensor faults, and bus communication errors. Events like corrupted firmware or sensor signal dropout can cascade into systemic failure, so each was modeled to support redundancy planning. This branch essentially models the structural failure of fuel tanks, which could compromise the ability to store and safely manage onboard fuel. We assess the left, right, and aft tanks independently, with failure events including overpressure, tank seal degradation, and structural compromise. These events could arise from manufacturing defects, operational overstress, or undetected maintenance issues, and represent critical contributors to fuel system safety. And finally, this branch focuses on fuel transfer functionality. Failures in pumps, valves, and fuel lines can disrupt flow from storage tanks to the refueling system. We distinguish between left and right drogue tanks paths and aft tank flow paths. By modeling these individually, we can assess the effectiveness of redundancy, determine the likelihood of single points of failure, and trace impact to mission level outcome.
Another approach for the FTA is to look at individual failure effects that were determined in the FHA. For example, the 3D vision system failure is separated out into potential subfailures, which helps us determine lower level probabilities that are required for some of the components, such as the screen, wires, and PDU. These probabilities flow up to 3e to the negative 7, which is lower than the FHA assigned probability. Again, For the fuel pod, the warp camera failure was identified as a failure mode from the FHA. Here, we match the FHA probability with 1.02 e to the negative 5 and separate out the states to lower level events. The main contributors to failure are electromagnetic interference, electrical system failures, and physical impacts. Following suit, the automatic load alleviation system was investigated, with many overlapping basic events to the higher level FTAs earlier. Those repeated events, such as clogs, collapsed pipes, failed valves, and overheated pumps, are assigned probabilities to ensure the overall failure probability meets FHA requirements. Circling back to the original high-level FTA, we can now provide probabilities to the overall PSSA FHA through these subfunctions. Keep in mind that more investigation is needed, especially since the overall failure probability remains quite high. Likely, this mandates stricter independence criteria and lower overall probabilities for the intermediate events. Drilling in, we can see the logic which combines all probabilities from the failure effects. Some of these probabilities are funneled up through the previous FTAs using Cameo Systems Modeler. It should be noted that the overall logic combining failure probabilities could provide misleading failure probabilities, since there is likely significant overlap in basic events. This directly ties us into our investigation into common mode analysis.
The next few slides go through one of the safety analysis processes we used that's found in ARP 4761, known as the Common Mode Analysis, or CMA. In complex systems like the KC-46 tanker, where redundancy is key for safety, a CMA helps us uncover hidden vulnerabilities. It's all about identifying single events or errors that could defeat multiple independent systems simultaneously, ensuring our aircraft remains safe and reliable. The CMA can be performed at the aircraft or system level. In this case, we are applying it to the aerial refueling system. A CMA is a systematic qualitative method that dives deep into a system's design, development, manufacturing, and operation. We're looking for common causes, factors like shared power sources, identical software code, environmental stressors, or maybe even human error in maintenance that could lead to multiple failures at once. The process involves tailoring detailed questionnaires, such as the ARP 4761 example found in Table M1. The questionnaire can be tailored and is used to gather extensive inputs from design and operations, identifying critical independence principles that the system relies on, and then rigorously evaluating those principles against every conceivable common cause. The process is normally iterative, and what we present here would be the first pass, with results fed back to the design to make the design more robust. So we've applied this rigorous CMA process to 3 critical areas on the KC-46 aerial refueling system. Using the information from the earlier FHAs, we chose the following 3 independence principles, focusing on the fuel transfer pumps, the communication systems, specifically used to communicate with the receiving aircraft, and the boom operator controls. Here we look at the independence principle for the fuel transfer pumps. For reliable fuel transfer to the receiving aircraft, we rely on primary and secondary fuel pumps. Our CMA scrutinized electrical power, hydraulic power, and mechanical and thermal concerns as shown in the table below. At this stage in a design process, there's not enough known about the system to look at operational or maintenance effects, so those were left out. However, later iterations of the CMA should include those aspects as well. This slide looks at the second CMA independence principle for aerial refueling communications. Maintaining clear communication between the tanker and the receiver is paramount. The CMA investigated the independence of primary and secondary communication channels. Key concerns addressed included shared software components, susceptibility to common electromagnetic interference, and reliance on single data networks. Solutions involve diverse software architectures, physically separate antennas, and using different frequency bands to avoid interference. This slide looks at the third independence principle for boom operator controls. The precise movement of the refueling boom is critical, so it does not make contact with the receiving aircraft. Our CMA for the boom operator controls examined the independence of primary and secondary control paths. So we looked at common hydraulic or electrical power sources, shared mechanical linkages, and potential human interface errors. Mitigations include redundant hydraulic and electrical systems, physically separated control components, and extensive human factors evaluations to ensure intuitive and error-resistant control layouts. So to wrap up the CMA, this is a vital tool for enhancing the safety, reliability, and overall robustness of complex aircraft systems like the KC-46 aerial refueling capabilities. It's a continuous process, ensuring that even the most subtle vulnerabilities are identified and addressed throughout the aircraft's life cycle. This process should be repeated once detailed design efforts have been performed to ensure that independence principles are still met.
Here we have our system-level Petri net for the fuel transfer probe failure. So you can see we have a fault in the fuel transfer pump, which goes in to diagnose the error source. From there, it can go to electrical power, hydraulic power, or mechanical and thermal. From there, we've identified likely failures, such as the loss of a single electrical bus, the loss of a single hydraulic system component, or a pump overheat. Since we have redundant systems throughout this aircraft, we will then proceed to the redundant system takeover. If the redundant system is successful in takeover, we will move to the upper right for successful mission continuance. If the redundant system takeover fails, we will have to abort the mission, as in the lower circle. The previous model details what possible failures could happen in the fuel transfer pumps and what mitigations we have identified as being present. If the mitigation is successful, the aircraft can continue the mission. However, if the mitigations fail, the mission must be aborted and the aircraft returns to base. What is different with this system level view versus the aircraft level view is that a failure of multiple systems causing the mission to be aborted would be viewed as catastrophic for the system. But at an aircraft level, the aircraft and the crew would be able to return to base, which reduces the threat level for the specific failure when looking at the aircraft as a whole. Here we have an aircraft level Petri net for loss of thrust. We have identified 3 separate systems that could cause this: the engines, the fuel system, and electrical system. For the engines, you can move from engine 1 or engine 2. Loss of one engine does not mean that you have a total loss of thrust for the aircraft. However, if it moves to the right to total failure, you will have a loss of the aircraft. For fuel systems, we will have redundancies. If all of these redundancies fail, you move to loss of aircraft. The same goes for the electrical system. If the redundancies fail, you can result in the loss of an aircraft. For the aircraft Petri net and for the loss of thrust, the aircraft level describes that the systems involved in producing thrust and the progressions of failure that would have to occur to result in the total loss of the thrust of the aircraft. Total failure of any of these systems not only results in the failure of the mission, but also the loss of the aircraft and possibly the crew, which is where the differentiation from the aircraft level and the system level comes up.
Thank you for joining us for our analysis of the KC-46 preliminary and system safety assessments. As system safety is inherently iterative, future work would involve refining fault trees, quantifying risks, and incorporating mitigations as the design evolves. Thank you again, and have a great day.